Hi, my name is Liz Tatum. I'm a graduate student at the University of Illinois at Urbana-Champaign, working with Vesna Stoyanowska. Today, I'll talk about my research on splitting BP2 BP2 at odd primes. First, I'll say a little bit about why one might be interested in doing such a thing, and then I'll discuss my results and current work. So, a central question in stable homotopy theory is to ask what are the homotopy groups of the spheres? Although this is intractable, lots of interesting patterns and structure have been found, and a family of tools that we can use to study that structure are the R-based atom structural sequences. So if we let R be any reasonable connective ring spectrum, then there should be an R-based atom structural sequence whose E1 page is the homotopy groups of copies of R smashed with itself, and it should converge to the homotopy groups of the R-completed sphere. If we choose R to be a flat ring spectrum, that is, if the homotopy groups of R smashed with R is just a sum of suspensions of the homotopy groups of R itself, then the E2 page has this very nice algebraic description. So, for example, if R is the mod P Eilenberg-MacLane spectrum, then we'll have the classical atom structural sequence. If R is the Brown-Peterson spectrum, then we'll have the Adams-Novikov spectral sequence. These are both very powerful tools for studying the homotopy groups of the sphere. They both have this very nice algebraic description of their E2 page, and they contain tons of information, but it's very difficult to compute differentials with these spectral sequences. So it can be helpful to consider other choices of ring spectra. So two choices of ring spectra that have been very productive are the real connective K theory spectrum BO for the prime 2, and the one truncated Brown-Peterson spectrum BP1 to study odd primes. So both these spectra make it easier to extract the V1 periodic structure of the homotopy groups of the sphere. Also, both these spectra have a vanishing line, so in a certain range, there's collapse at the E2 page. But the drawback is these spectra are not flat. So just to get to the E2 page takes a lot of work, but once you know the E2 page, you have a great deal of information. So just as the BP1-based atom structural sequence highlights V1 periodic patterns, it's expected that a BPN-based atom structural sequence should highlight VN periodic patterns. But BPN is not flat. So in order to actually use a BPN-based atom structural sequence, you need a very good description of its E1 page. So breaking BPN/BPN into finitely generated BPN modules can help to accomplish this. And those sorts of splittings were crucial in order to actually use the BO-based and BP1-based atom structural sequences that we mentioned before. And so there's a family of spectra called the Brown-Gitler spectra that are very important for constructing these splittings. So I'll introduce those next. So before talking about Brown-Gitler spectra, we need to define Brown-Gitler comodules. So to define Brown-Gitler comodules, we use something called the weight filtration on the dual-Steenrod algebra. So basically we'll say that the weight K Brown-Gitler comodule should be generated by all of the monomials in the dual-Steenrod algebra, having weight at most K. The homology of BPN is a subalgebra of the dual-Steenrod algebra, so for each n greater than or equal to 0, we can define a family of generalized Brown-Gitler comodules at that height n. So the weight K Brown-Gitler comodule at height n should be the comodule that consists of all of the monomials in the homology of BPN having weight at most K. So it's well known that these Brown-Gitler comodules can be used to produce splittings of the homology of BPN/BPN. So specifically, for every n, the homology of BPN/BPN can be decomposed as a sum of the homology of BPN tensored with the Brown-Gitler comodules from one height down. And for small values of n, these splittings can be lifted to spectra. When n is between -1 and 2, for each n, there should be a family of finite spectra, B sub n of k, called the Brown-Gitler spectra, which realize the corresponding Brown-Gitler comodules. When n is equal to 0, this splitting is realized by Mahowald. When n is equal to 1, Kane realizes splitting for BP1 smash BP1 at odd primes. And Kane's work on this was based on this closely related splitting of BO smash BO that Mahowald produced. It's conjectured that the analogous splitting should exist for BP2 smash BP2. And some further evidence towards this conjecture is the work of Dominic Culver, which says that the homotopy groups of the left-hand and right-hand side here are isomorphic. So the focus of my current research is to actually construct this splitting at odd primes. So next, I'll talk about strategies for doing that. So it can be shown algebraically that there's a family of maps, theta k, from the homology of the appropriate Brown-Gitler spectrum into the homology of BP2 smash BP2, such that if we lifted each of those maps to a map of spectra, then that will suffice to construct the splitting. So one way to do that is to show that the map theta k for each k survives this atom spectral sequence that lifts that homology map to a map of spectra. So we'll say that a class in the E2 page of the spectral sequence is a potential obstruction if it lives in a degree where a differential off theta k could hit it. So in order to show that theta k survives the spectral sequence, we need to show that none of the potential obstructions are actual obstructions. So as a warm-up to the BP2 case, I tried the BP1 version, and things work out very nicely there because there just aren't any potential obstructions to lifting these maps theta k. So that replicates Kane's splitting of BP1 smash BP1. And in very low degrees, it looks like you'll have the same thing for BP2 smash BP2. For example, at the prime 3, you don't see any potential obstructions when k is less than 27. But once k is equal to 27, you start to see many potential obstructions. There are lots of classes that a differential of theta k could hit. And the same thing appears to be true at other primes. But the good news is that there are only finitely many of these potential obstructions. So for each k, there are only finitely many potential obstructions to lifting the map theta k to a map of spectra. But these are still potential obstructions, and we need techniques to analyze them. So I'm currently employing a method used by Klippenstein to construct a splitting of BU smash BPN in terms of BU smashed with height 0 Brown-Gitler spectra. So the approach is to compare the atom spectral sequence, which is converging to maps from the appropriate Brown-Gitler spectrum into BP2 smash BP2, with a different spectral sequence converging to the same thing, called the universal coefficient spectral sequence over BP2 star. So basically, the approach is to show that all of the potential obstructions in the E2 page of the atom spectral sequence correspond to classes in the universal coefficient spectral sequence, which must survive. And so there are some complications to doing this for BP2, as opposed to Klippenstein's work with BU. But for very small values of k, I've shown at the prime 3, I've shown by direct computation that this comparison does work. So combining this with the lack of potential obstructions in very low degrees, we can say that at the prime 3, we can lift the maps theta k for k less than or equal to 28. So my plan next is to continue these direct computations for higher values of k, and also work to generalize this comparison to prove that this works for all k. Thank you.